Welcome to part 2 of our Aspen Plus video tutorials. So in this part, we will be going over the actual simulation tab of Aspen Plus. And I will only be going over what some of the units are as well as how to use them. I won't be doing a full-fledged simulation. If you do want practice for any full-fledged simulation, there's a great textbook called Learn Aspen Plus in 24 Hours by Thomas A. Adams. And they have 10 or 12 tutorials that walk you through an actual full simulation, and they also have the solutions online, although I do believe that they are Aspen Plus version 12 or lower, so the software will just prompt you to use the older version or to update it basically. So to start off with, here we have our actual simulation tab. So our flow sheet is empty at the moment, and at the bottom here we have our units. To be able to select your unit, you want to just click on it here, and you'll notice that the white background has moved from my mouse onto the unit itself. So let's start by adding just a material stream, like so, and we'll just call it 1 for now. And then we can switch back to the mouse here before clicking here and being able to set the parameters we want. So not every stream you will need to set every single parameter, especially if the streams are output streams. Aspen Plus will be able to set it. And you can also pick how you would like to define the composition. So let's do, for now, let's do half methane and half water. And then we'll say kilomole hour of 100. And then we can close this, and this stream is now defined here. Next, let's add another stream. Call that 2. As well as a mixer. Okay. To be able to connect the streams, you want to click connect here, and then it'll put it here. So whenever the arrow is in red, that means you must connect something, while blue arrows are optional additional connections. Also add a final stream here for the output stream to the mixer. And then we also do need to define stream number 2. So if you look on the side here, it'll tell us which streams or blocks we still have not fully defined via the red circles. And when things are not fully defined, you will also have the required input incomplete at the bottom here. So let's do similar here. And let's have this be carbon dioxide and oxygen. Switch this to mole fraction. Okay. Now we have all required inputs are complete, and we can run the simulation via the run button here. Notice we do get this error. And in this case, I know this error stems from the fact that we have used the wrong property package. So how can we get around this? First, we can go change our property packets, or there's another method as well. When you get an error like this, you can open the control panel. It will prompt you to open it, or if you do not hit the prompt in time, you can go over here to home and then control panel, and this will tell you exactly what the issue is. So you can figure out where the calculation failed based on what the control panel is telling you. So in this case, it's letting us know that they were unable to calculate reaction constant for MEA plus and MEA CO minus. So like I said, I know that this is because we've used the wrong property packages. So I will go over here in user models and click on hierarchy. Hierarchies allow you both to organize different parts of your simulation if there are clear subsections, as well as set different property packages for everything inside of that hierarchy. So let us for now copy paste this inwards. I do not suggest cutting because I have encountered issues when I cut different things, but if you want to remove something, I would copy paste and then go back and delete the other ones. So let's go into the hierarchy itself, and we will paste this here. And when inside the hierarchy, we can define its own property package. So the hierarchy block is right here. We'll click on this one here, and then under methods, we can come back to the property package selection that we had when we were under properties. So in this case, let's switch this over to Penn Robinson. And you'll notice here now we have an error at the bottom, but there are no red circles here. So in that case, we're just going to go back to properties and make sure everything's fine here. And we'll notice method has an error, and we'll click on parameters and then binary interactions. It just needs to load the new interactions that we added with the new property package. Returning to simulation, our hierarchy now has the property package of Penn Robinson, while everything outside of the hierarchy has a property package that we previously defined for the whole simulation. So now that we know this needs to be inside this property package, this hierarchy, let us delete it. And we can return to the hierarchy either by clicking on it or returning to its flow sheet. Each flow sheet will be called flow sheet with hierarchy. And to return to the main flow sheet, if you ever do close this by accident, you just click on view parent here. And this will return us to the main flow sheet. So now all required input is complete, and we can run the simulation, and results are available. So to be able to look at the results, you can either click on individual streams and click on results, or you can click on the block itself. The mixer block is very straightforward. It'll just take the streams and mix them. This will tell us the results of the temperature and pressure, and depending on the units, there might be different things on the results here. And then we can also click on stream results to be able to see the streams that we want here. We can also add other streams, but we do not have any, even if they're not related to the unit that we are using. One other thing to note is that when you are looking at stream results inside of the property package here, it'll say 1, 2, 3. But if you observe them outside, streams, it will be called the hierarchy name and then the stream number. So you'll be able to identify which streams are in which hierarchy, basically. So here are the results for our mixing, basically. And you'll notice all the units are not, if they're not what you want, you can click on them here and just switch to which you want. Or looking at the full units, we can also change the unit set under home and units here. So we're under the metric one here. We can switch it to this one here, and that'll adjust everything. And this will adjust everything for the whole simulation. So it is a good idea to set your own unit sets to whichever units you need. You can go under unit sets and then new. Let's call it user defined number 1. And then we can set everything that we want per unit. You can also search if there's a specific unit that you need. We have area per price, chromatic velocity, every single possible. We have all of them here, and you can set each one individually to what you would prefer your units to be. Let's stay with the SI units for here. And since we did change something, even if it was just the units, there is now a yellow input change at the bottom. And when that occurs, you can rerun the simulation and get rid of that. And depending on if you have previously run the simulation or if it's the first time opening the simulation will take less time because some things have already been run and it's only rerunning what you've basically changed. If you want to rerun all the way from the start, you just click reset. And then we can click run once more, and this will just take slightly longer depending on how big your simulation is. Going back to the stream results here, we can also export all of our streams and what we want the results to be. So if we open up mole flows, and we can open up mole fractions, for example, as well. And then from here, just clicking on the little corner will highlight everything, which can then be copy all. Ooh. You can open up an Excel file and copy paste over all of the necessary information. Like so. I highly suggest moving everything over to an Excel file just because it is a lot easier than waiting for Aspen Plus to open and your simulation to run every single time you need to look at your mass balances or your energy balances or even your temperatures or different units. And this Excel file, you can just export it to your OneDrive and look at it from anywhere. Okay. That is our first example here of a unit. So next we have the separator blocks, and the separator blocks will just separate things based on what you specify. So for example, the separator here, we can have 2 output streams. And the input stream can be from number 3 here. And then once we click on the separator block itself, we can specify for stream number 4, I want all of the water to go into stream number 4 only and nothing else. So let's run this here. Right. Stream results. And stream number 4 will just have our water here, and all of the water is gone from stream number 5. So the separator block is very useful when you need to separate something right away, but it is not a realistic interpretation of what is happening when you do separations. So that is all for the basic separator here, where you can just set how things will be split. Under Flash 2 and Flash 3, we have where we can set the temperature as well as the pressure during the separation itself, as shown here. And we can change what our flash type will be by setting the duty, or by setting temperature and duty, pressure and duty, and so on. For these separator blocks, it does specify what your output will be. So the bottom one here, if you hover over it, will tell you that it is a liquid, and the top one will be a vapor. So Flash 2 has 2 output streams, Flash 3 has 3 output streams, 2 liquid, 1 vapor, and the decanter has 2 different liquid streams, as it is a decanter. So in here, first liquid and second liquid. So I won't be putting those into the simulation for now, but just know that if you do hover over things, it will tell you what the stream is expected to be as well. Next, we can go into the exchangers. So in the exchangers, there's 2 main types that can be looked at here. There's the heater as well as the heat exchanger. Heaters are very versatile, as they can also be used as coolers, and they are quite easy to implement, requiring your input-output stream. As well as an optional third stream here for any water decanting. We can also add a heat stream to the heaters or coolers if we want to specify the specific amount of duty that is being given to it. If you click on the arrow, you end up with heat work power here. So we can have heat going in or heat coming out, depending on if we are cooling or heating. We can also specify under the heater exactly what type of heating we want. If we want to specify the duty directly here without using a stream, or if we just want to specify what temperature I will end up being at, or the temperature change. So let's increase by 100 degrees Celsius for now, and we can set it at a pressure of 1. And looking at the stream results here, we have our liquid temperature becoming a vapor at 200 degrees Celsius about. If a secondary heater is added, you can also specify a stream in between the two, connecting them here, which will force the duty of your primary heater to be what the secondary heater is outputting as well. This will allow you to simulate heat exchangers without having to fully use the heat exchanger, which could be useful if you're still unsure of where your heat exchanger will go, and if you still need to do different analyses to determine the best optimal composition for the heat exchangers. So connecting this here, and we can set this to be a temperature change of -50, let's say. Pressure of 1. And now if we look at the 4 to 7 stream results, we'll notice that it is no longer at the 200 that we set, but it is instead at minus 60 here for stream number 7, because we forced the duty of this cooler no longer to be determined by what our temperature was. You'll notice the temperature is now grayed out because you have that additional stream. And it'll be using whatever this cooler generates. So I have gone ahead and added an example of a heat exchanger here. And I have specified all the streams, but we will specify the actual heat exchanger together. So clicking on the heat exchanger, we'll notice that we can define whether what kind of model we use, such as cell and tube, kettle reboiler, and we can also define whether it is countercurrent or co-current. So for now, I'm going to keep it as the shortcut. And the Learn Aspen Plus in 24 Hours textbook has a very nice little review of co-current, countercurrent, shell and tube at the beginning of tutorial number 4. So let's set our approach temperature to 10. And we can specify here, keeping it under design calculation mode, we can specify the outlet temperature. So let's say 40 in this case here. And then very simply, we just run. So once we run that, we can double check our thermal results here. Looking at the exchanger details, we can look at the calculated duty of the heat exchanger as well as the required surface area for the heat exchanger temperature that we set. We can also look at the TQ curves, if you click on the button up here, and see at what temperature which duty will be required for each of the inlet streams, and you need to make sure that it respects thermodynamic laws. So instead of using a design specification, we can use a rating or simulation. The simulation one will allow you to determine your output conditions based on the actual size of the heat exchanger. So for now, we can copy the area that Aspen Plus calculated for the 40 degrees Celsius. And if we just remove the 40 degrees Celsius from here, return to simulation mode, and we can run that. Results available. Go into stream results, and we'll notice that while we did set the exchanger, the size of the exchanger, we still have our 40 degrees Celsius that we expect in this case. And the curve should look the exact same as well, as shown here. So what is the benefit of using a heat exchanger over 2 heaters, for example? Based on how Aspen Plus does its calculation, if we have another unit here, for example, which might result in a loop from the inlet of the hot and the outlet of the cold for the heat exchanger, for example, this might result in some errors if the inlet stream here is not being specified. While if in the case where stream number 4 was looped back through stream number 6, similar to what we have done at the bottom here, we would still be able to calculate streams number 5 and 6 through the value of this heater because it is not directly attached to streams 4 and 7. And I wouldn't need to over-specify my simulation, such as in this situation here. Moving on to the reactor portion of the units, we have 7 different types of reactors, as well as an electrolyzer, which we will not be covering in this tutorial. And of these 7, the 3 of them do require the kinetics to be known, while the stoichiometric and the equilibrium will require the reactions to be known, and the yield will require you to specify the yield of the output products that you require. So depending on what kind of project you have and how much information you know, different reactors will be more beneficial. The one I will be using for examples today is the Gibbs free energy reactor, which minimizes Gibbs free energy. So I've gone ahead and set up the Gibbs reactor here for a specific reaction, and we can look at it here under stream results where methane is being consumed to produce hydrogen as well as carbon dioxide, carbon monoxide, and the water is being consumed along with the oxygen that we put in. The next component I want to go over is calculator blocks, and calculator blocks can be found, close all this here, under flowsheet optioning and then calculator. By defining a calculator block, it will override any values that you manually inputted into the simulation based on your calculation. So we can define exactly how much oxygen, how much hydrogen, how much methane we want to be inputted into the block based on another component, for example. So if you want to limit the amount of oxygen, you can do it here via a calculator block. So let's define oxygen, and then we can just copy this down. Since methane will be the exact same, it'll just be a different component. Methane. And then under calculator, we can write oxygen is equal to, let's say, 10 times the amount of methane. Now that we've set our calculation, we can go into sequence and we have to define our import and export. So I'll be importing methane and exporting oxygen in this case. And if we run it, we can also recall that previously our oxygen was at 200. And if we return to our reactor, we can now see that our oxygen is actually at 10 times what the methane was here. And this does affect how things are being reacted. Oxygen is no longer being limited. And we can very easily go in and just switch it out here. Let's say we want it to be 0.2 in order to limit oxygen more. Run this once more and returning here. Now we have hydrogen once again being produced, and our oxygen is much lower in this case here. The next thing I want to look at is a sensitivity analysis, and this will allow us to determine how things will change in the simulation based on varying different parameters. So going under model analysis tools, we can go to sensitivity, and we can create a new sensitivity analysis. Creating a variable that we will vary. For example, we can vary different temperatures, different pressures, or we can even vary the input compositions. Although, if you will be varying the input compositions, you do want to make sure that you turn off any calculator blocks, as they will override the sensitivity analysis and cause some issues. So first, let's vary the pressure from a starting point of 1 to, let's say, 30, and let's vary it 10 times. And then I know I'll be varying the same exact block, and I'll just need to switch it to temperature here. And let's vary from 100 degrees to 2000 degrees. Again, 10 times. Then we will define which variables we want to see are affected by what we vary. So let's look at just the hydrogen composition of stream number 11, which is our output stream. For the component of hydrogen. Then we will just fill the variables. If you do change anything in the definition here, you do need to retabulate each time. And then we can run our simulation. And we have our results up here, as well as under the sensitivity analysis here. So here we have how the hydrogen composition in the outlet stream will vary based on the different parameters that we did vary. And we can look at a 3D plot just to see what actually occurs, like so. So we can see that hydrogen at some point does plateau. So then let's also look at a 2D plot. Going to results and hydrogen. And we can see at different parameters what the temperature will be. And here we have the pressure being varied. We can also just define the results curve differently to get a better idea of what is happening exactly. So if we look at how temperature changes based on the pressure instead, we can see here that as the temperature goes up, our hydrogen output does go up as well, but it does vary depending on the pressure. Okay, and that'll be all for this video here. I will see you guys in the next one.